Welcome to the GMAT 41's Calculus exclusive online lesson. In this segment of the GMAT 41's online class, we are going to focus on calculus strictly. When you talk about calculus, we look at the aspect of differentiation, differential calculus. We talk about integration, that's integral calculus. You see, one may ask, why calculus in the first place? What do I need calculus for? Well, at the beginning of everything, the application of calculus may not be that obvious to us, and we may just wonder, what's the essence of this dy dx, But the truth is this: as long as conventional institution is concerned, calculus is a prerequisite to so many courses in the area of science, the area of engineering, and of course medical sciences. And that is why we want to take calculus very seriously. Sooner or later, the application of calculus in almost every aspect of our life becomes even much more obvious. I've been able to put together sources that could help you appreciate why you should study calculus. Whether you are in O-level, that's secondary school, why it's important for you to take calculus seriously. As a matter of fact, in higher institution, in the field of science, engineering, medical sciences, I want to tell you that not having this idea of calculus from early stage poses a lot of challenge when you see yourself in higher institution of learning. And that is why we have this from the GMAT 41 in order to build students, and the basic knowledge of calculus, and of course prepare them ahead of the professions that they may be pursuing, of course, if you're already in higher institution, or they may likely want to pursue if you are in O-level, that's secondary school, preparing for higher institution of learning. Therefore, I encourage you all to take this calculus exclusive class from the GMAT 41 seriously. Now, what does it take to join this class? Very simple, nothing much. For those who register early, the registration fee is 1,000 naira monthly, and the classes runs on Monday, on Thursday, and on Saturday. And for this week, we are kicking off with the basics of differentiation. Starting first with one of the most important formula as long as calculus is concerned, of course, from which other formulas in other field of sciences may be derived from. The first principle. But before we move on into deriving differentiation from first principle formula, I would like us to get a brief idea of what calculus is, which of course is one of the major reasons why you should take this program seriously, this course, this part of mathematics. Calculus generally deals with changes between two or more quantities. Is that okay? Alright, now coming to our daily life, there is this statement many of us use, and you hear change is constant. Change is what? Constant. That simply means that in our life we cannot do without changes, Things keep changing. And this is because in this life, as much as everything is in one way or the other connected to another thing. For example, if you are part of this program, you are connected to the GMAT 41, such that whatever we do here in this study affects you. Am I communicating? And so calculus is an aspect of learning that deals with changes in things. And if we know that in life we deal with changes a lot because we are in one way or the other connected to one thing, it simply means that calculus is something to yearn for, to take it very seriously. I have these graphs on the board. Okay? The first one here is linear graph, a straight line graph. We just said, okay, this graph is defined as y equal to f of x. Alright? Nothing too much about that. And then the second one is non-linear graph. Non-linear graph. Of course, you can see the graph is a curve. It's no longer a straight line graph as this. You know, when you're dealing with physics, for example, in the aspect of motion, you encounter something like this when dealing with straight line motion, because you have things like uniform speed, uniform acceleration, uniform velocity, where you take what we call the gradient, that is the slope of the graph at any point that you want. Now I have these two graphs here on the board. I'm going to talk a little about this first one, and then we will focus more on this non-linear graph, because of course that is the area that calculus come in, differential calculus. Does that make sense? Let us look at this linear graph. Now you look at, I have this graph, and maybe you have these 2 points, point A and point B. I may ask you to tell me how y changes with respect to x. That is to say, as x is changing, how does it affect y? As x is changing, how does it affect what? Y. Generally, what we do is to draw something that produces a right angle triangle for us. We draw a horizontal line from this A, move this way, and then we're going to step down this vertical. We'll bring down this vertical line from B. Now if you look at this shape, from this point to this point and then come down here, you notice that we have a right angle triangle. And now we can find how y changes with respect to x. If x is changing, how it affects y. Because this is a straight line graph, it is very easy to find how changes in x affects y. And as a matter of fact, in this case of linear graph, the change in x affecting y is constant. What do I mean by constant? It means that the way that x affects y is the same all through for this graph. Because if I decide to say, okay, let me get that right angle triangle, say from this point to this point, you know, I can have something like this. If I say, okay, let me get a right angle triangle from this point to this point, are you following? I can have something like this. Any one of these that you decide to find what we call its gradient, its slope. Of course, gradient, slope is the word we use to show or to define how changes in x affect changes in y. So in this case, if I decide to find the slope, it would be as simple as saying that gradient, which of course is the same as slope, will be equal to change in y over change in x. Now this is the way we represent it. We are going to use n to represent gradient. Please take notes. Let me even introduce it here. Gradient n. Now this change in y over change in x can simply be said to be y2 minus y1 all over x2 minus x1. This is how we define the change. And that gives us the gradient n. That gives us the slope n. It simply means that if I want to get my gradient for this linear graph, all I will do is to come to my right angle triangle, get my final value of y, get my initial value of y. I'll do same for x. Get my final value for x and get my final initial value of x. Then their values, I'll just put them into this equation. And when I solve, it will give me a value, a constant, telling me how change in x affects y. Now we may wonder, how do we get our x1, y1, x2, y2? I'm going to quickly show you that so that we now get set to move on into this second graph, the nonlinear graph, and of course derive our first principle formula, okay? To get our x1, y1, x2, y2, which we will substitute into this equation to get our gradient, is simple. Now watch. Y is the vertical axis. So you come to your right angle triangle, alright? Now your Y1 is the beginning point of this right angle triangle of Y axis there, alright? The vertical line. Come to this point, then you trace it dot 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 to Y axis. The value here is what we call our Y1. The value it gives to you from the vertical axis here is what you call Y1. Do same, you come over here, you trace dot 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 dot. This will give you Y2. So initial value of Y, final value of Y. Simply take them to the vertical axis, to the Y axis. The same thing to get your X1, X2, the X is the horizontal axis, this is the initial, and this is the final from the right angle triangle. So you take it down to X axis here, you get your X1, and then the same thing here, the final point, take it down to X axis, here you get your X2. Is that clear, right? So actually, at this beginning point, we could just say this is X1, Y1 at this point A, and then this point B gives us our X2, Y2. So their values, simply put them into this formula, this equation, and then you get your gradient. Now, it's important for me to tell you something here. I've shown you how to get your gradient, which actually describes the way changes in X affects Y. Alright? This gradient is actually related to the tangent of an angle. Because if you look at the formula used in getting gradient, we said it is changing Y over changing what? X. Let me take you a little into trigonometry. A little into what? Trig, okay? Trigonometry. Now, if I give you a right angle triangle like this, just like you have here, now it makes an angle. This line, look at it, this line is our graph itself, this. Now, this is a right angle triangle. There is an angle here called theta. Now, this vertical axis, the Y axis, is called the change in Y. And of course, it is called the opposite when you are dealing with right angle triangle. Then this horizontal is the X axis, change in X. You can say that. And of course, we call it the adjacent. Adjacent. When you are studying trigonometry, okay, trig, we know that tan theta, and tan theta is tangent. So let me write it in full. Tangent of this angle, okay, is equal to the change in Y all over change in X. That is opposite over adjacent. That is where the word toa, comes into play. Why did I bring in this? Simply to tell you that when you have change in Y over change in X, which is our gradient, you are actually talking about tangent, alright, of an angle. Tangent. And when we talk about tangent, this tangent is actually a straight line that touches a curve at just one point. Is that okay? A straight line that touches a curve at how many points? Just one point. This is very important for you to know because we are now ready to move on into the second graph, the nonlinear graph. Let us now see how we study the changes in X affecting Y when you are dealing with a curve. The first principle. It is now time we are going to derive that formula in differentiation, a powerful formula known as the first principle. To do that, we're going to focus on this second graph, the nonlinear graph. But as we move on into deriving this first principle, alright, it is important for you to remember something. Our interest in getting how changes in X affect Y, simply how changes in one quantity, in one thing will affect the other one. We will be interested in what is called the tangent. That is what we actually established from this linear graph. Are you following, right? We are going to be interested in what is called the word tangent. And I told you that the tangent is just a straight line that touches a curve at one point. Now, let us look at this nonlinear graph. You see clearly that this point A and point B, drawing a line, that is joining this point A and B using a line, it is very clear that the line passed through the curve. It touched the curve at 2 points. This line AB is called the secant. It's called the word secant. A secant touches the curve at 2 points. But our interest, in order to get the way changes in X affect Y, our interest is in tangent. And so the question would be, what can we do to this secant to make it a tangent? Because it is only when we get a tangent, that we can be able to study very well the way changes in x affect y. Now I want to watch something. This line is a secant line, like I said, and I've told you the reason. If I want this line to become a tangent, I have to do something. Just watch. Imagine that I keep A at this point it is, and then I start adjusting B. Let us assume I bring B to this point. Okay? You know, if I join this point A and B, then the line will go this way. You will notice that the curve will close a little. Now watch again. I can decide to bring B down again. You know, I'm bringing it closer to A. And again, if you join these 2 points, you will notice that it will close the curve more. If I continue doing that, let's assume I bring B to this point. Once again, you will notice that I'm going to have a straight line like this, closing that curve even the more. My aim is to get a line that touches the curve just at one point. Now, if I continue doing this, I will get a better line that will get to a tangent. If I bring B even much more closer to A, you notice that the straight line will go this way. See, dear friends, eventually if point B gets to point A, if point B gets to point A, we are going to get a line that looks like this. Watch. This is how the line is going to look like. And if you look at this, it shows clearly that this straight line touched this curve just at one point, which is point A. This happens if B gets to what? Point A. So I'm going to indicate it at this point for this line. A is equal to what? B. That's to say point A is equal to point B. They are at the same point. And if they are at the same point, it means that their x value will be the same. That is, x1 will be equal to x2. See, when you had A here and you had B here, if you bring it down, you know, you'll notice that x1 will be clearly different from x2. As you move B down again towards A, you will see again that x1 and x2 will be clearly different. But if this B moves until it gets to point A and point B are at the same point, it means that x1 will be at this point, x2 will also be at that same point. Therefore, it means that for that condition, once this secant becomes a tangent, because this line is a tangent line, once that happens, at that point x1 will be equal to x2. And if x1 is equal to x2, it simply means that change in x, which is equal to x2 minus x1, will be equal to 0. Change in x, which is equal to x2 minus x1, will be equal to what? 0. What does this tell us? It tells us that if I have a curve, 2 points on the curve joined by a straight line, and it happens that the straight line cuts across, passes through the curve, we call that line a secant line. That line does not actually describe perfectly how the changes in x affect y. What describes how change in x affect y is a tangent line. Now, in order to get the tangent line from this secant, the 2 points must move closer to each other. The 2 points must move close to each other. And they will keep moving for you to get a better tangent line. They will move very close to each other, such that eventually if the 2 points now happens to be at 1 point, then you have gotten what we call a tangent. It is under that case that you can be able to study the way changes in x affect y very well. And I've shown you the condition at a point where point A is equal to point B, that is, they occur at the same point. These are the conditions. Initial value of x and final value of x will be the same, which means if you do x2 minus x1 change in x, it's going to be equal to what? 0 at that point. So once you get your tangent, that condition occurs when change in x approaches what? 0. You know, as this B is coming closer to A, it could be that you keep B at that same point and you are moving A closer to it. If A gets to B, eventually the tangent line will now look like this. Are you following, right? Eventually, when these 2 points get to a particular point, they become the same. Are you following, right? You see clearly that you've gotten a tangent, and of course, for this A to go towards B, or for this B to be moved towards A, it means that they are approaching zero. The difference between them is approaching what? Zero. My distance from where I am to where you are, let us assume it is 5. If I'm coming closer to you, the distance will be reducing. If I'm coming closer, the distance will be reducing. I hope you know that. So we say that it is approaching zero. There is a reason why I explained that to you, because by the time we get close to deriving this first principle formula, we are going to apply that condition. Now let us move as we derive this first principle. Are you ready? Now, for us to find out how changes in x affect y, we need a tangent line, is that not so? And to get that tangent line, I have told you that one of the points will have to approach the other one so that you get a better approximation. You get a better line that can represent what you're trying to study, called a tangent. And for that to happen, it means there will be change in x. And of course, if x is changing, y will also do what? Change. So I'm going to say that let there be a change in x, which will cause a corresponding change in y. And we're going to use delta x and delta y to represent them, just like I have this. Now you have this, delta x and delta y. We have this function defining this curve. The function is y equal to f of x. So given y equal to f of x, what we're now going to do is to see that as x is changing, y will also change. So we're going to add those changes to this y and f of x. When you come to this f of x, it is x that is changing. Are you following, right? So you are going to add that change to x. So this becomes x plus delta x. And now, I'm going to make delta y subject of the formula, because we want to get something that will much more look like delta y over delta x, because this is what describes how changes in x will affect y for us. To make that happen, I'm going to write delta y, making it subject of the formula, so this y is going to move to the right hand side. Please take note, this is not D. It is not D. Alright? It's a symbol for change, like triangle. Is that okay? Like triangle, something like this. Alright. We know that y is equal to a function of x, f of x, because that is what this curve is defined to be. Y is a function of x. So wherever I see y here standing alone, I'm going to replace it with what? F of x. So this becomes delta y equal to f of x plus delta x, then minus, in place of this y, I am going to substitute f of x there. Are you following? Alright, I have made delta y to stand alone just like this, delta y. We are trying to define our gradient, which of course is the tangent line, right? Remember that in this case, delta y was divided by what? Delta x. So we're going to do same there. We will divide through by delta x. And so we'll have something like this, delta y over delta x equal to all the right hand side. And then we divide it by delta x. Good. Now this equation you see here on the board defines our secant AB. Defines our what? Secant AB. And I said earlier that the secant does not tell us, alright, how changes in x affect y correctly. What we use in studying the way changes in x affect y is our tangent, not secant. Therefore, we will find a way to change, to transform, to convert this secant, are you following, right? This secant equation to tangent equation. And that brings us back here. Under what condition will a secant approximate to a tangent? Under what condition will a secant become a tangent? It happens when the difference between the 2 points that produce the secant for you. Look at, you have point A and B that produced our secant initially. Once the difference between the 2 points, in terms of the x value, are you following, right? The x value here is actually called the independent variable. I'm still going to talk about those anyway. Y is dependent on x. So we'll call y the dependent variable and x the independent variable. I am saying this because all this idea of x and y, they can be represented with any other alphabet. It's not compulsory that it must be x and y. Are you following, right? Besides, this x and y, like I stated from the outset of this class, they actually represent how things change. This x and y represent two quantities. In real life, it could be about temperature and environmental factor. How environmental factors affect temperature. So the environmental factors can be taken as one variable and the temperature be taken as another variable. Because in that case, temperature depends on the environmental factors. So the temperature becomes a dependent variable and the environmental factor becomes the independent variable. Remember I told you calculus is actually how things change. So in real life we meet all of these things. Is that okay? So we move on. If the difference between the 2 points in the secant line is approaching 0, then the secant will now be approaching, will now be tending to a tangent. Does that make sense? You have the secant. This equation defines the secant for us. Our interest is to get a tangent. Under what condition will the secant approach tangent? It happens if the difference between the 2 points on the secant approaches 0. And that difference I've shown you here, it happens when delta x approaches 0. Like when we are bringing this b closer to A, at every point if you check x1 and x2, you will take note that, or you will observe that the difference will be reducing until it gets to 0, and then you will get a perfect tangent. And I'm going to apply that here. That for this to represent a tangent, delta x should approach what? 0. And this is written in this way. If you take limit of this whole secant as delta x approaches 0, this will now become a better representation of our tangent, which of course is what we define as dy dx. Good. Now, if delta x approaches 0, this arrow is used to represent approaches. I follow intending to, getting to 0. Then the limit, this lim is limit of this whole function. Look at the limit of this whole term. As this delta s is tending to 0, the limit of this whole term will also be tending to dy dx. And this dy dx is actually what our gradient is all about in this case. Is that okay? And of course, I've told you that the gradient is also the same as the tangent. You want to call it slope, it's a choice. Is that okay? So that's the condition we're talking about. We can now conclude, therefore, dy dx is equal to the limit of all this secant function, which is f of x plus delta x minus f of x all over delta x, as delta x tends to 0. This is how we define it. And this is what we call the first principle. I'm going to indicate that the first principle. So whenever you are to carry out any differentiation from first principle, you can use this formula directly. This is the formula called the differentiation from first principle. You may choose to start that problem, solving that problem from beginning, just like I did here. You can choose to start doing this, and eventually, as you're solving that thing, you finally get your answer. Or you may choose to just pick this formula and substitute terms given to you, and again, you will get your answer. Now, I've taken my time to explain to you the idea of this dy dx. This dy dx is our gradient, is our tangent, is our slope, telling us how change in x affects y. We're dealing with a curve. Now, a curve, alright, is something that changes at every given time. Because this tangent I got here could have been gotten at this point. If point A was here and you bring in B to it, the tangent would be at this point. I hope you know that. If point A was here and you are bringing B to it, the tangent will occur here. So you see that along a curve, the tangent can be obtained at any point. That is the idea of the change. As you move from here to here, the tangent value will be different from here to here. The tangent will be different from here to here. That's the gradient, of course. I hope you're getting me right. That is not the same as this straight line. For this straight line, you can get it just at any point and it will be equal. But if you're talking about a curve, your gradient will be different at different points. For us to be able to solve such kind of problem, we use this. And of course, in real life, you know that because things keep changing, alright, this is actually what we need to be able to analyze such real life problem, since we know that every day, every time, things keep what? Changing. You have to memorize this formula, very important, and of course, know how we derive it. Like I said, if a question is given to you, you may be asked to derive it from first principle. You may choose to start it from beginning like this without question, or you might choose to use the formula directly. We are going to see how we apply this first principle formula.